In physics, we often answer the really big questions. Why is the universe here? Why is there more matter than antimatter? We're going to do one now. This is the big one. What is the force between two wires carrying current? It's been scrawled on cave walls. What is the force? So let's first draw our two wires here. One wire there, one wire there. And we are going to do the problem as though they're infinitely long, and one carries a current I1 and one carries a current I2, and they're separated by a distance A. Okay, so the reason there's going to be a force is this one's going to make a magnetic field here, and this one is going to feel a force because of that field. This one will make a magnetic field here. So the first step is to calculate the magnetic fields. And the notation that we're going to use is B x dash y, where that means B due to x at y. Okay? So the first one we should calculate is what is B 1, 2? What is the magnetic field created by 1 at the position of 2? All right. Well, we know it's a magnetic field due to a wire. We know that's mu naught I over 2 pi r, where r is the radius away. Okay? So B1, 2 will be mu naught I1. It's the field created by I1. Mu naught I1 over 2 pi. And instead of r, the separation actually is a. Right? Mu naught I1 over 2 pi a. For the direction, we use the right-hand rule. We put our thumb along the current. Our fingers curl in the direction of the magnetic field. Our fingers are curling into the board here. And why don't we go ahead and do this with a coordinate system. I know some of you really like the coordinate systems. X cross y, z is straight out of the board. There you go. So this one is in the the I hat direction, x-axis. No, of course, yeah. Sorry. This one is going into the board. Let's draw the vectors so that I can catch up. Here we go. Into the board, and it's in the negative k hat direction. There we go. That's what I meant. Okay, so now let's get B21. B21, well, it's going to be very similar. This is a magnetic field due to I2 created at I1, so it's also mu naught I2 due to I2 over 2 pi. It's the same separation A. Now we just see if I can actually get the direction right. Right-hand rule, thumb along I2 creates a field coming out of the board at I1. So it's in the positive z direction, so it remains positive k hat. So that's two magnetic fields. Now it's more complicated throughout space. Here this one is pointing in hard, it's a big magnitude close and it decays away, and this one points out with a big magnitude, decays away. Lots of stuff is happening, but at the actual position, we've calculated the magnetic fields. So next, let's do F12. Right? This is the force due to I1 on I2. Okay, so F12, then, let's think about it. We know that the force on a wire is IL cross B. So the force on I2 depends on its own current. So it's I2. Okay. And then L cross B. Well, L is the length of the wire of I2. We're actually going to calculate the force per unit length. On an infinite wire, the force would be infinity because it's infinitely long. So we're actually assuming kind of some length of wire like this, the same length for each wire. So we can call that L or L2. Let's just call it L. It's the same L. So it's F, L, and L in this case is the direction of the current, so it points up. And then L is going to be crossed with B. So if we have this up crossed with B in like that. Now it's crossed with which one? It's crossed with B12. the magnetic field due to 1 at 2. So B 1, 2, like that. So what we can do is plug in our value for B12 and figure out the direction. Let's see, so B12 is this, so F12 must then be I2 L, big L, mu naught I1 over 2 pi A. And now let's figure out what direction it must be. Let's see, L going along the current cross with B, it must be in F12, like that. So it's in the negative X direction. That's what I was thinking about before. It's in the X direction and it's negative. So there is F12. So if these things have current going this way, this one feels a force going in. Now, let's look at F21. Well, almost the same. It's going to depend on I1 rather than I2, because it's the force on 1, L cross with B. So L and the magnitude of B, you want the B here, that's B21. So it's mu naught I2 over 2 pi A. And if we want the direction, it would be, we're going along the current this way, up, cross this way. Oh, it's also in. So it's in the positive I hat direction. So the answer to the big question is that if you have the force between two wires carrying current, if they're going the same direction, it's in. And the amount is basically the same. You see they each have an I1 and an I2. They experience the same force, just in opposite directions. If you want to express it versus length, you just pull the F or the L, then you have force per unit length. So that's how you derive it. Now, let's see if it really happens. Okay? So here we have two wires, and they're going to experience the same current. We're going to let the currents be equal. And it's going to come out, and let's see, it's coming into this front wire here. It's going along here. And then I have this wire bringing it back underneath, and then it starts here and goes on the back wire. So I've set it up with this cross wire so that the current through the black wires that you're going to watch goes in the same direction. Okay? So if we flip on the power supply and throw the switch, we can see what happens, and sure enough, they're attracted. The two wires are pulled together like that whenever the current is on. Now, I can flip the switch the other way, and then instead of the current going this way, the current goes this way. But it also goes this way in both wires. So basically the current can both go this way and it's attractive, or the current can both go this way and it's attractive. Now you could ask, what if we had the current going opposite ways? Well, you could look at this and maybe figure it out. Really what you're talking about doing is flipping the sign of one of these currents. Say we flip the sign of I2. Then what would happen? Well, if we flip the sign of I2, suddenly this one would be positive. This wire would feel positive force, and this one would be negative. This wire would feel a negative force. If you flip the sign of one of the currents, it makes the force become repulsive. So I think I can do that. Let's see if I take this off, rather warm wire off here, and this off of here, and put it over here, and then this over here. So now the current comes in this wire, and then is just joined these two here, and it comes back. So now we have currents going the opposite direction. So let's see what happens. And sure enough, they repel. If I get them a little close to start with, let's get them nice and close and make sure they repel. Yes, either way I throw the switch, they repel. So the world makes sense. Now, there is actually a real reason that this is important. In addition to people wondering for millennia about this, there is an additional reason, and that is it is this equation gives you the definition of the ampere of the unit for current is defined in terms of the force of two wires. So if we imagine two wires, 1 amp each, 1 meter apart, we can calculate the force per unit length. Let's see, so F over L would be the current, 1 amp, times another current, 1 amp, times mu naught, which is 4 pi times 10 to the minus 7 over 2 pi times A, which is 1 meter. Well, the pi's go away. That becomes a 2. So in the end, the answer is 2 times 10 to the minus 7 meters. Newtons per meter is the force per unit length you get. So that's measured, and that means by definition, that's an amp. This is how it's defined, which also means an amp is a coulomb per second. This is also how you define the coulomb. It's defined in terms of measuring this force. So in the very first lecture, when I told you about 1.6 times 10 to the minus 19th, that's based on this experiment. This is how they standardize the unit.